Assalamualaikum warahmatullahi wabarakatuh. Today I will present to you about my project. Firstly, I would like to tell you that my name is Ahmad Hafizuddin bin Muhammad Tajuddin. Uh, and yeah, today I will present to you about my part, which is CANSAT in the structural part, which consists of the structural aspect of the CANSAT itself. So that's next. Okay, what? Why would I pick this topic? Yeah, because okay, maybe yeah, all of you already know. Some of us already participate in the CANSAT years ago. Uh, the first time IIUM sent a team, we get the third place in the national competition, and the second one, yeah, we managed to we managed to participate. And then okay, the first motivation, the first reason why I doing this paper is because we want to inspire the next generation, especially the next participants who would participate in the national CANSAT competition, to to make our journals as a reference, uh, for them to improve what is wrong with the already available CANSAT. Okay, and the second part also, I noticed that most of the papers published uh, in the most of the journals published, uh, they just publish the the CANSATs, the topic CANSATs, the CANSATs topic for the paper only talks about the mission itself. For example, uh, namely what kind of mission? Okay, for example, I also, yeah, I read one of the paper that in that paper the publisher, he he made a mission about analyzing the water underground. So he just he analyzed the aquifer underground. So the whole paper talks about that mission itself, not really about the hardware, the structure. Yeah, about that part they rarely emphasize on the paper. Also, okay, the third one is because we, yeah, no, the recently we noticed that there is an increase in participation of the national CANSAT competition. So we do realize, with the increase in participation, uh, most people will create something new. So it generates new idea. So of course, with the new idea comes the new innovation. All right. So okay, we also find the pain, not really pain, the problem in designing the CANSAT. First of all, of course, the CANSAT is constrained. From the name itself, CANSAT, can size satellite. The satellite itself, it is constrained to to the dimension of the can rings, and of course, the mass is 350 gram, which is approximately equals to the mass of the can rings also. Okay, and then also the thing that I noticed in the CANSAT is that uh, yeah, we all of us want the longer descent durations, because we launch CANSAT from most of the people, they launch the CANSAT using rockets, and then the rockets ejected the CANSAT, and then it descends. So what they want they want the descent times to be slower. So how how could that happen? the issue is, yeah, how could that happen? So how could that happen? It is it is the size of the parachute that helps to minimize that. And of course, when uh, when the body landed on the ground, we don't want anything happen to the body. So so the mechanical properties of the material, which the specifically want designed specifically used for the design of the body, we need to improve. And the last part, and the other problem is, we want the mission to be success. For our mission, specifically for our mission, uh, we made missions. We have two missions, two main missions, the primary and secondary. The primary, of course, it is consists of pressure, temperature, and altitude measurement. And the secondary mission, we propose that we want to do the solar array. And for this mission, we have to record all of this data in real time. So yeah, for that purpose, we need the CANSAT itself to be descent very low, not very low, very slow. Yeah, and also during the process, we want the inner hardware to be protected. Okay, now we go to the objective. Our objective, firstly, we want to, yeah, identify the mechanical properties, just like what I said before. The properties, the mechanical properties of the material, it is very crucial to design the CANSAT body itself. And also, we want to find the mechanical properties of the fabric also, because the fabric, we want it to be lightweight, and then we don't want the fabric to be easily teared. Okay, the second part, and next, the objectives. We, okay, to determine the most suitable canopy profile and the size of the parachute together with the length of the suspension lines. Okay, so all of these preferences, it contributes to what we call longer descent durations. Okay, and then the third part, of course, we want to design the CANSAT against mechanical failure. Just like what I said, we want the CANSAT, when it reaches the ground, the structure is still intact. Okay, so yeah, the CANSAT. What does it mean? It is obviously an acronym for CANSAT satellite. And how does it all start? Yeah, how does it all start? Yeah, the story is like this. During 1998, there is one conference participated by the guy named Bob Twix and several students from University of Tokyo, and also together with them there are one society called ARLIS. Yeah, it is the small rocketry group in America. So from that conference, they decided and discussed, and hence from that discussion, they decided to do the project CANSAT, and another project is CubeSat, which most countries are doing right now. So okay, after that event, the CANSAT was created by most University of Tokyo students, and it is launched in Black Rock Desert, Nevada, USA. Uh, the CANSAT itself is designed by the students. However, the sounding rocket, it is from the ALIS. Alright. Literature review. Okay. Now, the first literature review is, we want to review how does the CANSAT started in Malaysia. So in Malaysia, the representative from Angkasa, yeah, at that time it is called Agency Angkasa Malaysia. Right now it is called MISA, which pretty much the same. It's called Malaysian Space Agency in English. Yeah, during that time, during 2007, the representative from Angkasa, they participate in UNICEF, the UNICEF workshop. Sorry, it is International CANSAT workshop organized by UNICEF. And uh, from that workshop, they present to them about the idea of the CANSAT. Yeah, and since that day, the since that day, the Angkasa was heavily inspired, and several competitions in Malaysia has been done ever since that day. And yeah, uh, okay, the okay most of the competition we have primary mission, which is very compulsory, and the secondary missions, which is based on the participants' proposal, which is just like what we did, just like what did I proposed before. And then yeah, most of the CANSAT it is launched to certain altitude, of course the higher altitude, not reach the low Earth orbit. It is lower than that. So when it is launched, uh, definitely the CANSAT will fall to the ground afterward. So that's where we need the parachute. Okay, so the second, so this is the second part of the literature review, where we took them. Yeah, this is about material preferences, aluminium. Yeah. So okay, aluminium is used uh, is used in the CANSAT for many times. Most researchers, participants, they use aluminium for the CANSAT. It is can be directly obtained from can rings. Usually they using it for the casing, and yeah, the alloy the specific characteristic of alloy it has, uh, the aluminum alloy it has the improved mechanical characteristic compared to the original aluminum alloy, and it is categorized under the temper designations. Yeah, and this temper designation it has the specific characteristics. Okay, however, despite the high mechanical characteristics, it is a heavily electrical conductive material, and it it has the problem when it comes to the data telemetry transmission, because because we know that the aluminium people using it as the casing, and when they use it when they're using it as the casing, it forms something that we call Faraday cage concept, where the in the Faraday cage concept, the experiment is like this. The electrical field from the outside cannot really penetrate, cannot really influence the electrical conductive material inside the cage. So in this situation, the casing itself it becomes the Faraday cage. So that's the idea. And then the thermal it's also thermal conductive, which disturbs temperature recording. Uh, Basically, one of the participants from ESA competition. ESA stands for European Space Agency. Uh, from European Space Agency, they faced this problem. So because of this, the data seems very illogical. Okay. The second one, well, I want to talk is about the polymer. Polymer here is something like plastic. No, it is non-electrical and thermal conductive materials, and also it is lightweight and low melting temperature. Usually polymer is it is just like what we learned in the high school. Polymer is covalent bond covalent bond. Meanwhile, the metals, the aluminium, it is ionized bond. Okay. The most common polymer used for manufacturing, for the school project and stuff, for modeling nowadays, it is the 3D printed material. So the most common 3D printed material, it is ABS and PLA. Both of them use in the under the category of material extrusion. The fuse deposition modeling is one of the method of the material extrusion. So this is exactly the method that they use for 3D printing for these two polymer, because you know 3D printed material also used for another material, for example the steel, the the concrete, but most of them they didn't use this method. So okay, next, the polymer. Okay, now it is ABS. ABS is the type of material used for 3D printing. Okay, the characteristic of ABS, it has the higher melting temperature. Hence, with the higher melting temperature, it is easier to be manufactured compared to the PLA. However, the difference is not really quite far. Okay, but ABS, it has the lower mechanical characteristics. What I want to say here, mechanical characteristic, it defines as the yield strength, the ultimate tensile stress, what they are the okay, the Young modulus. Okay, so hence it is only suitable for the quite a little bit higher temperature environment than what the PLA might used to. Just the difference is not quite so far. Okay, and then now the PLA, of course, it has the higher mechanical properties. It has a higher Young modulus, higher yield strength. So now this is the data you can see right here. Okay, this is what provided from manufacturers. PLA, it has 3,500 megapascal, compared to ABS it's 2,000 megapascal. Yeah, and yield stress, we can see here PLA is much higher. Okay, now we can see the temperature. Okay, Tn is the nozzle temperature. Nozzle here is not like nozzle in aircraft, but this is the nozzle that they use for it is actually the tip of the extruder, of the material extruder itself. Okay, we can see here the nozzle temperature for ABS is a little bit higher compared to PLA. Just the difference is it's nothing much. Okay, right now, okay, this is what the data that they obtained from the experiment. Okay, so now for the parachute fabric. Okay, the parachute fabric, we have two possible candidates that is suitable, which is nylon and Kevlar. Okay, now we want to talk about nylon. Nylon, it has a low air permeability, which means the air cannot really go pass through the fabric. And then it is lightweight, of course, and then the elongation is quite high, which is 25% compared to polymer. Later we'll talk about the polymer. The percentage is not really high. This is 25%, which is the quarter of the original length. And then the melting, okay, and the nylon, it melts at 260 degrees, which is totally completely useless for aerodynamic heating. So most space agency, I mean the NASA, they didn't use nylon for supersonic applications. Also, the military applications such as the USAF, yeah, they didn't use nylon for drop parachutes. And then, okay, as they have the melting point right here, 260, of course the strength declines under the sunlight and hot environment. Okay, now we go to Kevlar. Okay, Kevlar is it has a very high advantage, but it is not really preferred most of the time. Okay, it has high strength to weight ratio, and then Kevlar 29. Okay, Kevlar 29 is usually the Kevlar type that is available for the fabric. Okay, it elongates up to 3.5% compared to compared to the nylon. Nylon has 25% elongation. Okay, just like Kevlar, it degrades. The strength degrades. However, however, during 19 no 19 260 degrees Celsius, it will of course the strength it decrease, but it still retain half of the strength compared to the nylon, which is they are total loss. And of course the volume, it saves the volume compared to the nylon. It saves the volume of the for the it saves the weight and volume for the parachute, the parachute itself. It is lighter than the nylon. Okay, so now, okay, this is the most, okay, now this is Kevlar nylon hybrid. This is the most preferred preferred carrot sorry preferred fabric, not fabric, the combination of both Kevlar and nylon is preferred by most researchers because okay, the strength to weight ratio of the Kevlar nylon hybrid, it is considerably high compared to the nylon. But yeah, it is lower than the Kevlar, all Kevlar parachute. Uh, why it is the reason why it is uh, the reason why it is recommended is because uh, the Kevlar, it has a higher strength, and then the nylon, it is the strength is low. I mean the elongation is high, although the strength is low. And now for the mechanical configurations. Okay, we start with the parachute. So yeah, for the parachute, of course, it is one of the mode for descent control. Uh, we we require the parachute to be designed properly because we want the descent descent we want the descent of the CANSAT to be as low as possible for the data telemetry precision. So when the graph is plotted, it is accurate. And now and then, of course, the canopy, the type of the canopy, it determines the direct coefficient, the direct coefficient, and the size, it determines the area. So the combination of both, it is actually included in the equations which are related with the drag force. So with the increase in the CD and the area, we could increase the drag force, which increase the duration for the descent. And now CANSAT. Okay, for our mission, we want the CANSAT to fall in the ballistic and low altitude. So it will be subsonic Hence, a solid textile parachute is chosen. And then another mechanical configuration for the CANSAT is that we included vent, which it helps to stabilize the attitude of the parachute. And then the suspension line of the parachute will be longer. So right here, okay, probably you don't understand the vent. Vent is the hole that we make on top of the parachute itself. Okay, now we go to the mechanical configurations for the body. Okay, for here, the the body we want the body to have a factor of safety ranges from 1 to 2 according to literature, since it has the dimension and weight restriction. And from another literature also, it is mentioned right there, the CG means the center of gravity. This needs to be located at the bottom of the CANSAT for the attitude stability. Attitude is different from altitude. Attitude is which means orientation. Yeah, the orientation. And then okay, from another literature, it says that the circuits is simplified into PCB for minimized space. PCB means printed circuit board. Uh, it is just like the miniaturized version of the circuits. Okay, and then we want, and then according to another literature, uh, for to prevent it from buckling, we need to impose structural idealization. So hence, the body is designed into semi-monocoque structure. So now, research methodology. For design procedure, we design the body into two separate parts, which consists of the outer shell and the inner ribs. And then the whole was made on top of the shell, and also the inner ribs, because we want to put the parachute right there. We want to allow the parachute to be inflated when the CANSAT is released to the ground. And then ribs is divided into three sections, from the lightest at the top to the heaviest at the bottom. And the ribs, it is divided into three parts, which is the parachute compartment, the hardware, and the battery. And now for the parachute, we simply just pick hemispherical canopy for the profile. Okay, why we pick the hemispherical canopy? Actually, the hemispherical canopy is not does not contain the highest drag coefficient, but actually it is the most common profile used for the for paratrooping. For yeah, we can name many. They all use hemispherical canopy. Mm, okay. Okay, now, okay, after we design, we will do some analysis on both of the body and the parachute. From Okay, now we can simply use finite element modeling uh, using ANSYS. Okay, for you. So by using finite element modeling, we could find the elongation. I mean the strain of the individual components, and the next we can find the von Mises stress. Von Mises is actually the yield stress. Yeah, it is the yield stress, and then the buckling of the model itself. Uh, and also we could find another parameter. Yeah. So in conclusion, yes, despite the limitation, I mean the weight and the dimension limitation, the structure of the CANSAT could be improved with the continuous research for the structural optimization. So yeah, right now for structural optimization, we already have uh, the iso grid, the ortho grid, um, the rib structure, just like we have in the aircraft. We also we could add the strangers and so on. Okay, so thank you very much.